Okay, so this video is going to be about the frequency response and eigenfunctions for LTI systems. Okay, so we finally have enough material to say exactly what the frequency response is. H of omega, what the frequency response is of an LTI system. And all it is just the Fourier transform of the impulse response. H of t. Okay, i.e., in other words, H of t is a Fourier transform pair with the frequency response, H of omega. So this kind of justifies why we've been using little h and capital H for these two concepts. Okay, and so I'll just list out all the formulas, all the Fourier transform formulas with these functions plugged in so you can see. Okay, so we have our inverse Fourier transform formula. So H of t is the inverse Fourier transform of H of omega, the frequency response. And the frequency response, H of omega, is the Fourier transform of the impulse response. Oh, sorry, this is d omega, dt. Okay, so this is actually what the impulse response is. If you take the impulse, or sorry, what the frequency response is, it's the Fourier transform of the impulse response. So I give you an LTI system, you put a delta function into it, you get the impulse response, the output from that impulse, the response to that impulse, h of t, the impulse response, and then you take the Fourier transform, and there you go, you have the frequency response, h of omega. Okay, so if you have either one, the impulse response or the frequency response, you can get the other one. And so, since we saw in the last video that h of t completely characterizes an LTI system, okay, we can get the output from any input knowing just h of t. Well, the same can be said then for h of omega, because you can always take the inverse Fourier transform and get h of t, and then do the same thing, find the output to any input. Okay, it turns out, as we'll see in the next video, okay, there's kind of two main methods to getting the output from an LTI system. You can either stay in the time domain, use the impulse response and convolve it with your input to get your output function in time, or you can go into the frequency domain and use the frequency response and the Fourier transform of your input to get the Fourier transform of your output. Okay, it's just going to be the product of the Fourier transform of your input and the frequency response. I think we saw this in a previous video. The output Fourier transform is the input Fourier transform times the frequency response. Then you can just take the inverse Fourier transform to get back to time. Okay, so we'll see this in the next video, kind of two main techniques of getting the output of an LTI system for a given input. Okay, but for now, we're just focusing on the frequency response here. Okay, that was just a little preview. And so now that we have this definition for the frequency response, let's actually verify that that eigenfunction property we've been using everywhere to get outputs to LTI systems, let's verify that it actually holds for LTI systems. Let's verify the eigenfunction property holds for LTI systems. Okay, and using what we've learned so far, it's actually not too bad. All right, so just to be sure that we're on the same page, this is what we want to verify, that when I put in e to the j omega t to an LTI system with frequency response h of omega, I want to make sure I get out h of omega times e to the j omega t. We've used that all over the place. Now let's actually verify it. We have enough material in the class to do so. Okay, and from the last video, actually, I'll just start a new page. Why not? So from the last video, we saw that the output y of t is the input convolved with the impulse response, just like this. This is convolution. Okay, sometimes as a verb we say convolved. This is the input x of t convolved with h of t. That just means we perform this convolution integral, okay, using x and h. And there were two forms for this convolution integral, two equivalent forms. I'm just using this one for now. Okay, it's going to make the answer work out nicely. Okay, so how do we get the output? Okay, well, let's put in what our x of t is. There, x of t is e to the j omega t. That's our input. So now I'm just going to evaluate it at t minus tau. So everywhere I see my t, everywhere I see my t argument in my input, I'm just going to plug in t minus tau. I'm going to get the integral of e to the j omega t minus tau, and then times just h of tau, d tau. Okay, we don't know what actually the impulse response is. We're doing this in general for any impulse response. Okay, so now what can I do? Well, I can split up this exponent. And I can say, all right, e to the j omega t, I can take that out because it doesn't depend on the integration variable tau. So I'll bring that outside, e to the j omega t. And what am I left with? I'm left with h of tau, e to the negative j omega tau d tau. And that's what's left, e to the j omega times this negative tau. But wait a second, have we seen this before? When I scroll up, maybe I can get them both on the same page. Yeah. Look at this integral and this integral. They're the exact same. I just have a different integration variable, but that doesn't matter. Yeah, they're the exact same integral. So this down here is exactly the frequency response. It's the Fourier transform of our impulse response. And so there you go. We have verified now the eigenfunction property holds for LTI systems. Okay, and so now everything we've done so far about getting outputs to certain inputs when the input is a Fourier series or a Fourier transform, it all makes a lot more sense now. Okay, so that's all I had for this video, and I'll see you in the next one.